So one of the 47% female professors in chemistry that we have today is Greta Patzke. And back in 2008, when we celebrated the 175th years of inorganic chemistry at UZH, Greta and myself, together with Heinz Berg and Roger Alberto, we were actually covered by chemia. And at that time, Greta had just joined the department as an assistant professor for solid-state chemistry. In the years since, Greta has continued to be an outstanding researcher. She studied chemistry at the University of Hanover, finishing in 1997, and just 2 years later, she received her doctoral degree summa cum laude. In 2007, Greta joined the UZH with an SNF Förderungsprofessur, and in the years since advanced through the ranks and is now full professor and also a great colleague at the Department of Chemistry. So her research covers a wide range of techniques for the characterization and targeted design of functional molecular and heterogeneous materials, and all serve to address current environmental and health challenges. Greta led the University Research Priority Program LightCheck, solar light to chemical energy conversion, together with other colleagues. It's also better known as the EuroPP artificial photosynthesis, where they're using solar light, water, and carbon dioxide as the sole source for sustainable production of fuels. Based on this idea, she and colleagues from the Department of Chemistry participated also in the Century project of the Werner Siemens Stiftung. And so that was the competition marked the WSS 100th anniversary in 2023 and offered the prospect of quite a lot of funding for an innovative interdisciplinary research project on the sustainable use of resources. Greta and her colleagues were among the 6 finalists, granted 1 million Swiss francs to develop their ideas. And so also they came finally third in the competition. They continue to actively develop and follow these research ideas. And I think, Greta, this is also what you're going to talk us today. Thank you very much. Please.
Thanks again for having me here today. And the purpose of this talk is to give you something. First, I want to give a big thank you when starting this talk to the people and the university who made it possible, what I'm going to show today. But I also want to put you in the know in chemistry, because everybody's talking about green energy and green hydrogen and so on, and the take-home message here is that you know how it goes. Because I'm going to talk about catalysis, and catalysis is a pretty tricky topic, and in our group we go down to the atomistic level, to the very chemistry of this, atom by atom, mechanism by mechanism. And today I've been hearing about Edith and Lydia, and sometimes I wonder, what would they say to this chemistry? How would they judge the chemistry I bring compared to the possibilities that I have and have been given? Now that's a philosophical question for the upper row. I feel seeing Edith complexes that I fall even a bit short of this, but I leave you to judge this. Okay, today we're gonna start about clean hydrogen and water splitting, and first a big thank you to my group and to all alumni, present co-workers, everybody who worked hard to make this possible, and also to the University of Zurich, who always had faith in us, gave us a lot of support, as well to the Swiss National Science Foundation and several other funding agencies. A joint, diverse, and funny success story is for sure the URPP LightCheck to be seen here, and we were a happy bunch of people. We still are, as long as we are still at university, and we have a huge footprint in terms of young researchers, older researchers, third-party funding and papers. Okay, and our joint goal was to split water. And today I'm going to bring you 3 chapters of this talk. The first to set the stage a bit about why we want to have green hydrogen and what it takes. I'm going to focus on the good old electrolyzer technique today that you know from school probably. So what's new in there? I also thought the same, why fuss around with electrocatalytic water splitting, but there are many, many things that we still don't understand on the way to pricey green hydrogen. And the success stories today are not so much about people, but about the elements. We are looking into the atomistic workings of the catalyst and see what makes element pairs or even triads successful, how they work together, what they can do for us and what we can do for them in synthesis. And it's a bit of a tightrope walk. Should we be inspired by nature or by chemistry or by technology, but enough of that. Why green hydrogen? For many people, it's still a red flag. They don't want to hear of this. But anyways, I think if we want or not, we have to face the fact that we need hydrogen. We will need hydrogen in society and technology, and most of it is gray. It's like gray weather going on, and huge CO2 footprint. And what we need and what we research on are low-cost catalysts to bring the price for green hydrogen down that's generated by electrolysis with renewable electricity. So, and this is a slide to remember, maybe if you don't already know. It's ashamed because we have a big need for green hydrogen in the hard-to-abate sectors that you can't electrify fast. There we need green molecules, and these sectors are horrible. They eat a quarter of our energy consumption, and as a thank you, they spill out a fifth approximately of the CO2 emissions. And this is where green molecules and at the first part of the food chain, green hydrogen comes into play. And last intro slide, making the green hydrogen is quite an endeavor. I think we all become thirsty at some point, looking forward to a drink, stuffy air, hot room, and this is stable. We are water. Water is life. Why should it be split? And exactly, for doing this, you need a high uphill reaction. This sounds meager, but in terms of electrochemistry, it's a lot, plus extra taxes in here, and a good catalyst to shuffle the electrons around to really persuade water to fall apart into H2 and O2, a process that we don't observe normally. But it happens, not without knowing it, in photosystem 1 and 2, in nature, but nature had millions of years of time of evolution to come up with a molecule, I will close with analogues of this molecule, that still has drawn in, and was generations of chemists and so many labs worldwide. The first intellectual shortcut that we made, we and others, was to say, oh, we're going to rebuild this inorganic core of photosystem 2, and then we do artificial photosynthesis. But this wasn't so easy. What I'm going to show you was a different analogy to nature that I stumbled over. As you heard from our dean's remarks, I had a long career already, and sometimes the meanings and the opinions you have are very fixed. But when I entered electrocatalysis, I thought, solids are stable, there's nothing going on with them. In electrocatalysis, we saw quite the opposite. The big parallel I'm going to draw to nature is the so-called restructuring. You start in electrocatalysis with rock-solid stuff, oxides, nitrides, perovskites, what have you, and then they start to fall apart. And this falling apart and being reborn, restructured, is a trait of nature. Photosystem 2's core is also restructuring all the time. It's very resilient. And this is, to me, the connecting issue in chemistry, that we need to figure out this flexibility and resilience of compounds. We know this for sure, it's a trait, but we don't know yet how to trigger it and how to use it fully. And this is a fussy affair. We need a lot of technology to look at something as simple as a nanocube shown here. So the bars are high for electrocatalysts. We want convenient synthesis, we want it all. Low-cost materials, we want easy restructuring, as I mentioned in before. I'll introduce you exactly to what that is. And on top of that, a single catalyst making both H2 and O2. That's a lot, and it's a tall order. And then we want to do it ideally on the benchtop with low cost. So those are the catalysts, and this is what it takes to see what's going on with them. It's so-called operando. We really need to snapshot, like I'm being shot right now, snapshot the catalysts while they are splitting water, right? We need to look into the atomistic structure at the moment they split water, and this is not easy to do. Some of these techniques can go to the lab. We are working on this, but mostly we have to go to international synchrotron facilities and use high-energy radiation, beamline spectroscopy to capture what's going on in the moment of water splitting, and then retro-design our catalysts. And those spectra are not very friendly, not very accessible, but we get the information out. So, second part, success stories of the metal pairs. What is going on between them? This is the synchrotron and gray novel, and a lot of mountains still to climb, science-wise and otherwise. And yeah, cobalt and iron is the first story. So now, we were not the first, and we will not be the last group to work on this. What are they doing together? So what we add as a twist to this chemistry is beautiful morphology. Chemistry is also, I think, to a large extent about beauty, admit it or not. Nice molecules, nice colors, perfume smells, nice shapes, nice cubes. And so in here we were first doing the nice cubes, and then we put cobalt and iron together in them, and then we were observing catalytic synergisms between cobalt and iron. They could only do together what they couldn't do alone. And the spectroscopy we do at the beamline is almost a mystery still to me. I know it works well, but from this coffee ground wobble, we can conclude on individual atoms and their oxidation states and configurations. And this is also very popular in biology. Enzyme centers, other compounds that are beyond hope for classical X-ray, that are disordered, distorted, can be made accessible and understood on the atomistic level with that kind of spectroscopy. And yes, now the story of cobalt and iron. We put them together in this nanobox cage, and then we had the idea to vary their partners. Mostly they are coming along as oxides, but nowadays in catalysis, the concept is trickling in that oxides are not the leaders anymore. Others, like sulfides, selenides, tellurides, phosphides, are sometimes better. But we all know from the lab, or many of us, it's not so agreeable. It's stinky, sulfur chemistry, phosphorus chemistry. But we actually bit the bullet and had a very convenient procedure to making those cobalt iron phosphide nanoboxes. And they ticked all the other boxes for criteria, doing oxygen release, hydrogen release, working well, and looking good, being crystalline in the first place, crystalline by the book. You see the atomistic planes here, the structure, the elements sitting in their place. This is how it should be. Okay. And then we benchmark the catalyst. We see, are they better than noble metals? Can we do the mission of replacing them? How do they compete to our colleagues and peers' work? Is it okay? Is it not okay? This was definitely an okay for these catalysts to be moved to the beamline. This looks a bit homemade. The actual stage where they are mounted to watch the operando spectroscopy going on. It's a lot of fumble. It's days and nights of work, thanks to my colleagues who trashed many weekends, actually, to go there and do it with complementary spectroscopies, and you have to pack your suitcase, literally. You have to bring all reference compounds that answer your questions about cobalt, iron, oxygen, and phosphorus, and measure them in one go. Otherwise, you can't reach a conclusion. And the conclusion we reached was a weird one in the first place. This is a part of the structure. On the hydrogen evolution side, everything was good, almost. We peeled out with this spaghetti salad EXAF spectra, excuse me, but it seems very inaccessible. But when you retrofit them to known models and have complementary spectroscopy, you can really get down to the structure moiety. And this one here assisted hydrogen making. A lot of the initial phosphorus made the catalyst good, and cobalt and iron here, yellow and pink, also made it good. On the oxygen evolution part, the anode, everything was distorted. All the phosphorus had been thrown away. We couldn't find any of that in the post-analysis. The structure was different, and it was all about oxygen. And this is the restructuring. We entered catalysis with a totally different catalyst, and then we thought, is this detour really necessary? Do we have to do this to us, to the catalyst? Can't we just use this takeaway, put cobalt and iron, and start right away from nanoboxes that look like the product of the restructuring? But this was an intellectual shortcut. It didn't work. In fact, what is also necessary is to bring cobalt and iron to valences that are hard to get by in the lab. Show me a cobalt-4 complex stable on the benchtop. I think this wouldn't happen so much. Even Edith and Lydia would have a hard time coming up with that. And so this is necessary, and this high valence plus those moieties were just slow to come in the phosphorus-free compound. So we need to go that long road, phosphorus in, phosphorus out, let the catalyst find itself, so to speak. And this restructuring, disorder, and phosphorus loss was obviously necessary. You can play this game also with other chalcogenides and so on, and we are now researching deep into, and others too, into the means and the meaning of this process. Now, I'm going to be quick here. You see, it's a congested thing to analyze a whole solid in its bulk. It would be so much more elegant to have the atoms isolated, like on a surgeon's table, like in single dual atom catalysts. And it was a bit crazy in our group that we wanted to enter this field because half the world was working. But the goal that we had is looking at nickel and iron. They are the best success story. There's probably no better combination to make oxygen than nickel-iron catalysts. But why? Books and review articles are filled by theories and ruminations about this. And now we decided to isolate the individual atoms, investigate them, put our hypothesis into this field with unknown, at that time, dual atom catalysts. And again, this is a combination of hard bench work, hard in-house tests, and then beamline to come to a full picture. And the synthesis was the trick. In fact, you spread them out like thin butter on a bread on like planar C3 and 4 graphene-like compounds, and then the microscopy must show that the individual atoms are like little bloops here. Little bright spots, can't tell if it's nickel or iron. This is a bit of a problem, I admit, straight up. But here, no clusters, no coming together, no nanoparticles really spread out. And glucose, of all molecules, helped us with that. Tell me why. Glucose in a cheap protocol, after lots of optimization work, brought forward these catalysts. And individual atoms are better to understand and to study. The synergisms and success of nickel and iron, together they performed quite well in electrocatalysis. Benchmarking came back well, and so on to the beamline and tracking the individual atoms. Now these spectra are then Fourier transformed, and from these humps and bumps, under bias, you can see how the atomic distances change, how the pairs come together. And then we saw that nickel and iron were approaching, forming an active NiO Fe moiety that assisted the catalysis very well. The last word isn't spoken here, because we still have to give a more detailed atomistic explanation as to how they come together. We could see it. We could see it in the post shots. We had hypotheses which were spectroscopically confirmed later on. And based on this, also with the help of theory, we had a sound model to our view how nickel and iron made oxygen evolve faster. It's pretty complicated, as many things in catalysis, but it held up, and we could put our dent into this research area. So now, end of the talk already. I want to ask the question, or answer the question a little bit, does this nature-inspired cubane chemistry that's so alluring still make sense? And to us it does, but in a different way. We are having a more like integrated picture of solid-state chemistry. There is no difference to our view. There are molecules and solids, and they are all parts of a big compound family. So if you look closer at the cubanes, they are basically cutouts of oxides, which are also, as I said, great catalysts, and this is the high-resolution picture, and you see that today we are considering them more little brothers of big oxides than nitrous replicas. So our philosophy is make it on the bench, make it in large amounts, and make it pure. And then we can only start catalysis. For the cubanes, this was possible. Surely our crystals won't end up in the Royal Society gift box, but maybe you still can have wishes open. But they hold up, I think, quite well on the bench, and so we can make a spoonful if you wish. So it's not a given for many of these complexes at all. And so, yeah. So they worked well in photocatalysis as a sideline note, but now I'm trying to connect them to electrocatalysis, because they are doing good on the electrocatalytic side, but not as cubanes. And the allure and the goal is to keep electrocatalysis also molecular to enable better studies. These solids are so hard to get right. Why not study cubanes? But they come together and do the read-through pathway, go back to an oxide fast on the anode. And so we had an idea, borrowed a little bit from organic chemistry this time. They call it their protecting groups, and I don't know how you call it in inorganic, but for sure we put on such a linker here, a propionic acid substitute, and blocked some of the cubane sites to make them less prone to form an oxide lattice. This was a nice idea from my co-workers, really good. And even the first protecting group showed that the electrochemical stability was better. So the decline in current that shows the onset of this oxide formation didn't happen. And then we were spinning this tail, a blend of polymer and inorganic chemistry further, by saying, okay, why don't we protect them by putting into polypyrrole? It's a great conductive polymer. That isolates the clusters, we put them covalently bound into the polymer, and then do electrochemistry, hope they live longer, and they do. It's not perfect, but we are coming closer to a new chapter of the molecular electrocatalysis, to really observe molecules under electrocatalytic conditions and use the power of molecular tuning better in electrocatalysis. I admit that it is not easy to do the full analytical procedure in here, but at least we had several boxes ticked. The whole thing was more conductive, as we could see from impedance spectroscopy, better charge transfer, and in the end we also came to a mechanistic idea how the oxygen is being formed. And the last, I should say, maybe even scientific suite towards the end of the talk was a blending of it all. So now we heard about nickel and iron, which are working well, about cubanes, about oxides, about electrocatalysts, but it came to our attention that nobody had published a full-blown nickel-iron cubane. Why not? Again, the devil lay in the bench work, I have to say, in retrospect. It would tick so many boxes. There are nickel-iron enzymes, there are the oxide catalysts, there's the tuning opportunity, everything. There's more to it even. So, after, I should say, a year in the glove box, our group, I don't block anybody in the glove box, but technically it happens. But our group came up with that. I hated it myself, I have to say, one personal note. I hate it. So I admire this even more, that our group managed to come up with the first iron-nickel cubane, pure, beautiful chemistry, to our eyes at least. You see the cuboidal motifs and the ligand holding it together, and as a bonus track also an iron for the comparisons, beamline, and deeper understanding. That's now open to the community for inspection and doing what we did. If they are faster than us, bad luck. But we published it out with this. And then a last scientific question seems so trivial, but so hard to answer. Where are iron and nickel in the cubane? If I had made a hand-waving choice, I would have probably chosen before, with the yellow iron, with the nickel on opposite positions on the faces. But you have to prove it. That's science. The X-ray is blind towards the neighbors in the periodic system. It can't tell apart cobalt, nickel, and iron properly. So this was another big run down to the beamline, a long detour, and with the help of Sandra's group also, we got that basically figured out that C4 is best fitting with the spectroscopic results, and then we could put the full structure on the table. And now we are working with it. Others are hopefully picking it up, and the last slide is devoted to the landmark idea. We heard about Alfred Werner today, and about the brilliant females working in these days. I wonder what they would say to this kind of chemistry. We are now winding up with a whole zoo of not mononuclear cobalt complexes like Werner isolated, but cobalt cubanes. We don't do much ligand variation, but we get them in so many structures, different types we discovered. And the devil lies here in the fact that we are so behind organic chemistry. Organic can do everything, retrosynthesis, planning, and in inorganic we are a bit helpless. Still, after so many years, 100 or more years after we do the reactions, we mix them, and we are happy with the crystals, but we cannot plan it based on mechanistic knowledge. And I'm standing here being a bit uncomfortable saying this, but it's true. And it's a lot of hard work in our group going on, trying to figure out why these cubane types are formed with a tiny bit of preparation that's varied, how they are formed, what's the kinetic time scale, what are the mechanisms. It's a huge amount of work. I'm not confident if I can make it. As you heard, I haven't much time left, technically. But for this task, I should say. But we are hopeful that we have a foot in the door already on how this goes down. And it's amazing. And I think this is what inorganic chemistry needs, a fresh kick on this mechanistic side. We can live without it, maybe, but we need the full scientific picture, in my opinion. In our group, it's all in full swing. I want to thank the university again also for the ICA and the easy XHAFs. That's splendid. It's the first step to a mini synchrotron at home, but it's not the full picture, of course, but makes us much more efficient when traveling and preparing. And we are working on all these circles, starting from the transition metal centers and ending day and night in the new building. Thanks also for this. It's amazing. I heard about cellar rooms and basements today. We are lucky, especially in summer. It was so great on hot summer days. And day and night we're working on Elche campus and hope to continue what was started with the first female PhDs. Thank you.
Thanks a lot, Greta.